This is chapter 13.1. We're introducing sequences. Our life will be easier on the second and third section here, where they'll actually give us formulas that we can use to easily figure out the patterns. Today is more about puzzles. We're trying to figure out the pattern. We need to know a little bit about sequences and how the notation is. So the first term, we have a name for that. It's called a sub 1. And there's a subscript there, not an exponent or anything. And this would be the second term would be a sub 2 and a sub 3 and so forth. If there was a last term, we might call that a sub n if we don't know what number term that is. So if there's a last term there and there's a dot, 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 that means there could be a whole bunch of terms in between the fourth term and the last term here. And so that's what that dot, dot, dot would mean. So the first thing we're going to do is we're going to start with an explicit formula. I know you might know that from music. Doesn't mean there's any bad words in this formula. It just means it's an explicit formula. So there's another type we'll learn about in a minute, but it prescribes an exact way to get a sequence. And so basically to find, say, the first four terms here, we know that that first term would be called a sub 1. So what we're doing is we're plugging in 1 for n here. So if we want to find a sub 1, we just basically say, okay, that would be 4 sorry about that. There we go. Times 1 minus 2, which is 2. So the first term is 2. And then to find the second term, it's just a matter of plugging in. So a sub 2 would equal 4 times 2 is 8 minus 2 is 6. So our second term is 6. And then to find the third term, we plug in 3 there for 4. So 4 times 3 is 12 minus 2 is 10. And to find the fourth term, 4 times 4 is 16 minus 2 is 14. Sorry, I've had a little trouble with my stylus here. It's the best I can do here for now. Need to get a better stylus. I just got this one today, though. And it just started raining. I don't know if you can hear that. The second explicit formula here is kind of like a different equation. When you have, y equals 2x plus 1, y equals 4x minus 5. So it's a different sequence we're going to build here. So the first term, we're plugging in. So a sub 1, we're going to plug in 1 there, so 2 times 2 to the first power minus 1 would be 2 minus 1 is 1. So the first term happens to be 1 in this case. The second term would be 2 squared minus 1, which is 3. Third term would be 2 to the third, it's 8 minus 1 is 7. And 2 to the fourth would be 16 minus 1 is 15. Let's see, wait a second. 2 to the fourth is 16 minus 1 is 15, that's right. 2 to the fifth is 32 minus 1 is 31. So that would be this particular sequence. Notice it's a little different. When we have something to the nth power, we're getting a different kind of sequence here. Here, this had a kind of a real linear feel to it because it's a linear equation. Here, this sequence definitely has a different feel to it. It doesn't have a common difference between each term. We'll talk more about that. So find the nth term of this sequence. So they really mean find an explicit formula. Notice these formulas both started with a to the nth. A to the nth, that's considered the nth term. So when they say the word nth term, they mean a sub n equals. So first let's look and find the pattern here. That's what today's all about, looking and finding patterns. So from 2 to 5, you can see that you definitely have to add 3 to go from 1 to the next. From 5 to 8, we're adding 3. From 8 to 11, we're adding 3. So each time we're adding the same amount. That's a classic arithmetic sequence here. So our formula is going to be a sub n equals, I'm not sure what the whole formula is, but I'm adding the same amount every time. Notice we're adding 3 every time. So when you write your formula, you know there's going to be n is the number of the term there, so like n, a sub 1 is the first term and so forth. So every time n increases, the function increases by 3. So in this case, we know it's going to be 3 times n will be in this problem. 3 times n. In other words, every time n increases, a sub 1, a sub 2, a sub 3, a sub 4, the value is increasing by 3. So 3 times n is going to be the formula. And we've got to figure out what's being added here. And so I like to think of the very first term. In other words, we know this is true when when n is 1. So if we plug in 1 for n, we should get a value of 2 here. So I might try to solve this equation, kind of think of it this way. If a sub 1, if we're finding a sub 1, then 2 will equal 3 times 1. It's a terrible stylus. Plus blank, or plus x, let's say. So if you solve this, subtract 3 on both sides, you get negative 1 equals x. I'm going to use my finger instead here. I think that might work just as well. This stylus is really not working for me. So x equals negative 1. That should work. Let's test and see if it works for the second, for this next. Let's test the fifth term here. So if I want the fifth term, a sub 5 equals 3 times 5 minus 1. So let's see if this works. It's 15 minus 1 is 14. Does that look like it fits the pattern? If I put 14 in there, 2, 5, 8, 11, 14, yes, I add 3 every time. So it looks like we found the explicit formula. So that's the nth term, which is the explicit formula for this particular sequence. Let's try another one, see if we can get this one. This looks a little tougher, by the way, kind of a challenge problem. That's what tonight's homework is all about, seeing the pattern here. So when you go to the next term, you can see that you add 3. Next term you add 5. To get the next term you add 7. There's a pattern there, but it's not adding the same term each time. So I can't use kind of my normal pattern. Take a step back and look at this pattern. Do you recognize anything about these numbers? Sometimes it helps, if you're having trouble with this section, to think through and say, okay, a sub 1, a sub 2, a sub 3, a sub 4. I actually write those out and kind of looking at these. 1 goes with that. 2 goes with that number. 3 goes with that number. 4 goes with that number. So when n is 1, it's 1. When n is 2, it's 4. When n is 3, it's 9. When n is 4, it's 16. Now if you see the pattern there, but it may be more obvious when you look at it that way. So it looks like we're taking n and putting it to the, what are we doing there? We're squaring n, aren't we? So I wonder if that would work. A sub n equals, it looks like the next number of the pattern would be 25. Looks like these are all perfect squared. 2 squared is 4, 3 squared is 9, 4 squared is 16. So if I plug in, say, a sub 5, I get 5 squared, which is 25. So that does work. So that's a good pattern for that one. It's kind of a tricky one. It's not arithmetic. It doesn't go up by the same amount every time, so you really had to think about that one. Recursive formulas are a different kind. It's different than explicit, and these are actually easier on the brain. They're easier to think through, but they require some other thing here, which was not included here. So they always have to give you one more bit of information. They have to give you the first term. Let's say they gave you the first term was 7. So we have a sequence here. The first term is 7. Just given information. They have to give you 2 bits of information for recursive formula. The formula and then the first term also. So basically they're saying, when they say a sub n minus 1, it's real important you know what that means. So they're saying plug in the next term. So if we want to find a sub 2, I'm going to plug in for that. I'm going to say a sub 2 equals a sub 2 minus 1 plus 6. Now a sub 2 minus 1 is what? What is that equal to? Well, that's a sub 1. 2 minus 1 is 1. A sub 1 is 7, so 7 goes right there. So A sub 2 is 7 plus 6. What this really means, this is 13 then, is when you see this, this basically means the previous term. If you think of it that way, it'll make a lot more sense to you, the previous term. And so if you just take the previous term and add 6 to get to the next term, this would be 19, and this would be 25. And you can see you're just adding 6 every time to get the next term. Here's multiplication with the previous term. So again, that's not enough information to do a problem. Let's say they say a sub 1 is equal to 3. Now we have enough information to build this sequence. We know the first term has been given to us, it's 3. The second term, again, all you're doing here is you're basically saying this is the previous term, right? So if I want to find out this second term, I take the previous term, which is 3, and multiply it by -2, I get -6. To get the next term, I take -6, multiply it by -2. Again, this is the previous term right there. So -2 times that is 12, times -2 is -24, and so forth. That's how we build a recursive sequence. Let's try to write one. Again, I think it's kind of easy to write recursive sequences. So this would just be a sub n equals a sub n minus 1. I know I'm going to have that in there. That's a -1 there. Previous term plus what is the next term? Well, every time you're adding 5, and so that would be our formula. Partial sums are not hard, not difficult. They're based, but they're kind of a weird notation. So when you see this, it means sum or add up the first 3 terms. So when you see S sub 3, that means we're summing up the first 3 terms. So you're saying 1 plus 3 plus 5. So S sub 3 equals 1 plus 3 plus 5, which is 9. If they said, what is S sub 7? Well, let's do one that we have there, S sub 5. S sub 5 would be 1 plus 3 plus 5 plus 7 plus 9. So 16 plus 9 is 25. And so you can see all you're doing is adding up the first 5 terms, or first 3 terms, or however many they ask you to add up. It's probably the toughest problem we've seen. And this would be using the nth term to generate a sequence. Wow, do you hear that? So this would be, the first term would be a sub 1 equals 1 over 1 minus 1 over 1 plus 1, which is 2. And 1 minus a half is 1/2. And so then applying the second term, I get 1/2 minus 1 over 3, which would be, let's see, 3/6 minus 2/6 is 1/6. And a sub 3 would be 1 over 3 minus 1 over 4. That's 4/12 minus 3/12 is 1/12. And so to generate the sequence, so I've generated at least 3 terms of the sequence here. And if I want to find, say, a formula for the partial sum, so you want to look at the pattern you're seeing here with the partial sums here. So let's look at the pattern, see if we can think this one through. So S sub 1 would equal 1/2. That's the sum of the first terms. S sub 2 equals 1/2 plus 1/6. That's 3/6 plus 1/6, which is 4/6, or in other words, 2/3. S sub 3 is when I sum up the first 3 terms. All 3 of those terms added together, that would be 6/12 plus 2/12, that's 8/12, plus 1/12 is 9/12. Well, 9/12, when you simplify it, is actually 3/4. So I don't know if you're seeing a pattern here. I hope you might be. So we can try to say the formula for S sub n, just like we did with A sub n. We know the A sub n formula already. We don't need to find that. But S sub n should be a pattern here if we can identify it. And so the key is, I think, on this kind of thing, is to look at this, say, how does that affect this value? How does this affect this value? How does this affect this value? So it looks like to me every time that the numerator tends to match that. So I think the numerator is just basically n here. When s is 3, the numerator is 3. When s is 2, the numerator is 2. When s is 1, the numerator is 1. And the denominator seems very similar as well. When s is 1, the denominator is 2. When s is 2, the denominator is 3, and so forth. So I think this would be our formula, n over n plus 1. And again, I just identified a pattern. In this case, the pattern came from the partial sums.